Okay, so yeah, I'll talk in this presentation about chromium sulfide bromide. You've heard a lot about this already. I'll discuss particularly the excitons in this material. So that is what I think for spectroscopy, optical spectroscopy people, is what really drives the interest. This material is a magnetic material that has very, very strong excitonic signatures. So this is just good because we can use these excitonic signatures to track properties and investigate properties of these excitons in a magnetic material. And we haven't been able to do that, let's say, 3 years ago. So these Fenner's magnetic materials in that respect really have changed a bit the physics of excitons and their coupling with magnetic order because they're now accessible to experiments in these materials. So we can use our standard techniques and just see how the excitons behave when they're surrounded by magnetic order. So in this presentation, I'll show you a couple of experiments that I've been doing in the last 2 years or so, studying the transport of excitons in chromium sulfide bromide. And with this material, again, this is something that we really like to do because it's a magnetic material that has strong excitonic signatures, which means for the first time we can basically think about and also investigate the process of how an exciton, when it's created by a photon, actually moves through this crystal. Like, what is the process behind this motion? How fast is that motion? These are all things that we really, when we started out, we had absolutely no clue about it because there's just no previous work on this topic. So this is, for us, being interested in exciton transport, something that we've investigated in semiconductors and other materials, is just a very interesting question. So we feel like we've learned a bit about what processes can be involved. And so I'd like to present the results of this study here. So yeah, when I say we, I actually mean Sophia, Alexei, and me from Dresden University of Technology. We're working on the experiments together with Akash, Misha, and Zacha, who provide, let's say, help us with some theoretical support and get a bit of better microscopic understanding of the processes involved. And then the materials come from Zdeněk and Ksenia. With these materials, of course, we're only able, because of them, to do these experiments. So chromium sulfide bromide, we've heard a lot about it. Just to remind you, when I say excitons in this material, I really mean these sort of spectral features in the near infrared part of the spectrum of this material that can be very easily seen, particularly at low temperatures. So you can see here this sharp sort of resonance, the strong resonance of the exciton in the reflectance contrast or the derivative of that signal. So this means here light is absorbed quite a lot, which means the exciton oscillator strength is large. And that's good, that's what we want. And then you can also see this emission spectrum, and particularly here, there's this one peak that matches quite well with this resonance, and then there's a whole couple of other peaks that are not too important for now, let's say. Okay, so just very briefly, like one thing that I particularly have investigated before I started working on the exciton transport in chromium sulfide bromide is the coupling of the excitons to light. So as I said, their oscillator strength is really large, which means these excitons like to interact with light. And one thing that we sort of figured out quite some time ago now is that the excitons in bulk crystals particularly couple even strongly with the light that is confined by these bulk crystals, and then you get all of these polaritonic properties. So that's something, if you take a crystal that has a thickness of 100 nanometers or so, the excitons strictly within the light cone don't exist. So you should really think of this more in this picture of exciton-photon coupling in polariton language. Now, to study the transport of excitons, I really want to steer clear of this effect. I'll try not to have this as much as I can, which is why I limit all of this study to these very thin crystals that you've seen before, like the spectrum from a 10-layer crystal, for example, that is more or less like the boundary to where particles, optical quasiparticles, are, let's say, clean and pure excitonic. If we add more thickness to the crystal, if we just take a 50 nanometer crystal, already there's significant mixture with the photon, and that sort of messes up my experiment. So I really want to steer, look at these very thin crystals. It's very important. There's a couple of other interesting properties of the excitons, but one that is important for this study, I believe, I'd like to highlight, goes back to work from Eunice Bay in Xiaoyang Shu's group at Columbia in 2022, where they showed with this really, for me, very important and impressive experiment too, that the excitons and the magnons in this material are coupled. So here you can see how this coherent oscillation of the magnetic order, the spin wave that processes coherently, modulates the energy of the excitons in time. So that's a very important phenomena. It's also important for the physics that I'm going to show in the rest of the study. What we learned in this when working with the polaritons is also something that I think is a bit less easy to understand at first glance, but it's also very important. If the excitons couple to the magnetic order and they couple to the coherent magnons in this material, it's not too difficult to figure out that this sort of a random oscillation of the spins, it doesn't have to be a coherent excitation, it can be an incoherent excitation, a fluctuation, also couples to the exciton. So basically whatever you do to the magnetic order, as long as you bring it out of this equilibrium antiferromagnetic order, it will couple to the excitons. And in this model, we sort of figure out the math of the angles and stuff. You find out that if your crystal is in an antiferromagnetic phase and you increase temperature, which means that you incoherently start to induce these thermal fluctuations of the spin, you'll get this redshift of the exciton as a function of temperature. But if you force the magnetic order into a ferromagnetic configuration and then let them fluctuate and whatever they like to do, this will actually lead to a blue shift of the exciton. So this is a sort of a prediction that we made based on a model. And then we realized, well, if we want to compare that to the experiment, then we have to include the phonons. But then we end up with a sort of a model prediction that looks like that. And it turns out when we actually look at an exciton-like polariton branch, for example, as a function of a magnetic field and temperature, this is in reasonable agreement with what we see in the experiment. So the excitons in chromium sulfide bromide couple to the coherent magnons, but they also couple to these incoherent fluctuations of the magnetic order. I think this is also really relevant to understand the physics of the excitons. So in chromium sulfide bromide, we have found a material that has excitons that couple very strongly to light. They couple with the magnetic order, excitations of that magnetic order. And then on top of that, we've already seen that quite a bit, especially in Mike's talk. The electronic structure is also highly anisotropic of this material. So all of these are good reasons why we're so interested in understanding how the excitons, once they're created, actually move in this crystal. So just to very briefly introduce the way that we do this experiment, everything we sort of expect when we create the excitons, how they move in most semiconductors, the typical process is classical diffusion. So it is very much the picture of a drop of ink in water that just disperses over time. This is just diffusive transport. And because the masses of electrons and holes are anisotropic in this material, we can just calculate the anisotropy ratio of the diffusion coefficients. So we expect that within the plane, along this easy axis where the effective mass is fairly light, we get a 10 times higher diffusion coefficient than along the other direction. So we expect this anisotropic diffusion. This is really what we had in mind when we started these experiments. So we shoot these laser pulse to create a symmetric distribution of excitons, and then as a function of time and space in this experiment, we can sort of track how the width of that distribution changes along the A and along the B direction. And because of that anisotropy, we would expect that this distribution grows faster along the B direction with the light mass characterize the excitons, and then we don't expect to see much along the A direction because they're really heavy, 10 times the free electron mass. Very heavy exciton, shouldn't move so much. So that's what we expected to see when we started out. Now I'd like to show the sort of the key parameters of this study, and I believe the most important one is actually what happens when we look at this diffusion coefficient, so how fast the excitons move in this material as a function of temperature. We can again sort of calculate this classical expectation where you can see this anisotropic diffusion, and we can actually make this sort of quantitative. So these are the numbers that we expect for the effective diffusion coefficient. When we look at that in the experiment, the result looks quite different. So when we track this effective diffusion coefficient, we see this increase towards the Néel temperature, and then there seems to be a maximum sort of in the vicinity of the Néel temperature, and then it continues to decrease as we go to higher temperatures. So it looks like, particularly at the Néel temperature, the excitons move the fastest away from the excitation region. So this is the first key result of this experimental study. We see this maximum at the Néel temperature. So I'll show you some more results of exciton transport at this Néel temperature, particularly what happens when we look at the transport along the B direction of this crystal for different excitation fluents. So when we start to increase the fluence, you can see here the solid line, or the slope of that line, that represents the diffusion coefficient. So when we increase the excitation fluence, the slope of that line increases, and it sort of continues to increase as we apply more fluence. We get a higher effective diffusion coefficient. So this number increases. So the second key result is that the transport of excitons at the Néel temperature is fluence dependent. The more light we shine, the faster the excitons move away from the excitation region. The third key result is sort of hidden in this number. So this number, 150 centimeters squared per second, is actually pretty large. So it's a really large number if you compare that to most semiconductors that we've studied in the past. This just means the excitons move very fast, much faster than they should, based on like any classical expectation about their diffusion. Okay, so far I've only discussed this transport along the B direction. Because the effective mass is anisotropic, we know that from band structure calculations, from ARPIS, from many other signatures. We really expect that the transport along the B direction should be much faster than along the A direction. However, when we do the actual experiment and we repeat these measurements along the A direction, a sort of surprising result was that the exciton transport seems to be almost the same along the A direction. So there's no like huge differences between the A and the B direction, which means that the exciton transport appears to be nearly isotropic in chromium sulfide bromide. It's another result that was not really expected in the beginning. Okay, so these are all fairly interesting results from our perspective because they're not expected. They're also very robust results. We've repeated these experiments with different crystals. It's really like a very solid, each of these observations is very solid. So we're trying to understand what mechanism actually drives the transport of these excitons, because clearly it's not the classical diffusion as we had expected in the beginning. Something else must be at work. So in order to motivate this model that we have developed, I'd like to briefly sort of consider what it means when we shine an ultrafast laser pulse on a magnetic semiconductor like chromium sulfide bromide. So we, of course, know that we shine this non-resonant laser pulse to create the density of excitons. That is very clear because we see the light that comes out from these excitons, so we know our excitation works. We do also know from a lot of previous work on other magnetic materials, or more specifically here from these works, that optical excitation with very similar conditions that we use in our experiment creates an excitation of the magnetic order. So people have used that to study the transport of excitons in this material. So if you sort of image that in this semi-silly simulation here, you can kind of imagine that after a certain time there's a wave, a magnon wave that is propagating away from the excitation region, and that actually happens both along the A and along the B direction of the crystal. So you shoot light, you locally maybe heat your sample, there's different processes could be involved, but definitely you create a density gradient of the magnons that leads to a propagation of the magnons in this material. So in order to understand what the excitons actually do and how they move in the crystal, we believe that we have to sort of account for both phenomena. The light pulse creates excitons, but it also creates magnons, and they're propagating. How does one affect the other? So the simplest process that we can think of in this context is very much analogous to a process that is very well known in the context of the thermoelectric properties of magnetic materials. So if you heat or you apply a heat gradient to a magnetic material, then in many systems people observe what they call the magnon electron drag effect. So here we're simply proposing the excitonic analog of this phenomena. So the basic idea is that when you shoot a laser pulse, you locally create excitons, you locally create magnons. Now the magnons are going to move away from that excitation region very fast. And because the excitons and magnons are coupled in chromium sulfide bromide, the magnons can actually scatter the excitons. They can impart momentum. They sort of push the excitons away from that excitation region. So this is the sort of the general picture that we have in mind when we think of these experiments now. And we feel like this allows us to explain sort of the key signatures that we see. So first and foremost, we observe this maximum of exciton transport at the Néel temperature, and that can be rationalized because the conductivity of magnons in antiferromagnets is actually very generally enhanced at the Néel temperature. So the more conductive the magnons are, the more they will accelerate the excitons. The more light we shine, the more magnons we create. Again, the more we accelerate the exciton. That sort of explains why the exciton transport depends so much on the excitation fluence. It is also kind of interesting to note that while the exciton motion should be fairly slow in this material. We do see very fast transport of the excitons, and if you play out the numbers, it actually matches quite well with the kilometers per second that have been reported for the propagation speed of the magnons in this material. And then last but not least, again, it's interesting to see that the exciton transport should be highly anisotropic because of the anisotropy of the electronic structure. But if you look at what the magnons are doing, their propagation is actually fairly isotropic. So that's how we argue we see isotropic exciton propagation because the magnons are moving isotropically. So with this general idea of the magnon-exciton drag effect, we believe that we have found a reasonable framework to sort of account for these very interesting experimental phenomena, again, in a semi-reasonable way, I would say. So this captures a lot of the phenomena that we see at intermediate and high excitation fluence and throughout like a large temperature range. So to sort of conclude this presentation, I just want to briefly mention that there's two fairly striking experimental phenomena that occur exclusively when we go to very low excitation fluence and very low excitation temperature, not true, very low temperature and very low fluence. So we're really trying to create this more a low temperature environment. And then there's two things that we see that are quite super surprising, I'll say. So one thing is that when we look at the transport of these excitons in a bilayer sample, and this is very specific for a two-layer chromium sulfide bromide crystal, instead of like a regular, more or less diffusive expansion of the mean squared width of this distribution, we see what we call a super diffusion. So this is not we call it that, this is just what it's called when the width of a distribution of particles decreases super linearly in time. So you can see here this clear behavior that deviates from a linear increase in time. And we do see that, again, it's very robust. We see it for the ferromagnetic configuration of the bilayer, as well as for an anti-ferromagnetic configuration, also for the A and the B direction. So there's a superdiffusion of excitons exclusively happening in bilayers, because if you move the laser spot from the bilayer to just a nearby trilayer crystal, this entire behavior is gone completely. So you can see here in the bilayer, the increase, or the velocity is just significantly larger, and all of this super diffusive behavior is gone. And then the second sort of striking phenomena that we do see in chromium sulfide bromide at low temperatures happens when we move even further to a 10-layer crystal, again under the exact same experimental conditions. We see, instead of this fast expansion, we see a contraction of the exciton cloud. So we see this sort of negative transport, and the excitons are now no longer seem not to be moving away from the excitation region. They're sort of pulled backwards. So this is, again, a quite kind of interesting phenomena to observe, and it's very rare to see that in this type of experiment. Okay, so as I've mentioned, these two phenomena are definitely, currently we don't really understand what's happening. The only thing that I can offer right now is sort of to speculate how, in a magnon drag picture, we could maybe try to understand these two phenomena. So regarding this superdiffusion of the excitons, one could, in principle, think about the process where the laser pulse creates a magnon wave, but the magnon wave now just propagates ballistically at low temperatures. It's like a coherent propagation, even on very fast timescales, and that just drags along the excitons. That would, in principle, account for the fact how excitons can move basically ballistically through a crystal. However, in order to make that explanation work, we really have to understand a bit better the properties of magnons in two layers, because the velocity of excitons that we see is actually so large that it exceeds the velocity of magnons in bulk crystals of chromium sulfide bromide by about an order of magnitude. So we really have to understand a bit better what it means to have magnons in a bilayer crystal compared to a bulk crystal before we can make like solid conclusions about this magnon drag in two-layer crystals. The contraction is very interesting because very recently the group from Joseph Orenstein published a paper where they investigated particularly the role of dipole-dipole interactions for this material. And their conclusion was that magnons with a very small wave vector actually have a negative group velocity in this material. So we're thinking about the idea, what that means when we create magnons with a negative group velocity that would, to us, seem to be a magnon wave that where the phase front propagates outwards, but the group velocity and the momentum of that wave actually points inwards, which means that the excitons would not be scattered outwards, but actually inwards. It would give you this negative drag effect. Instead of pushing them away, it'll sort of be pulling them towards the density gradient of the excitons. So that's definitely like an explanation we're exploring at the moment. Okay, so with chromium sulfide bromide, we were able to look at the transport of excitons in a magnetic material. We did start out with a classical or expectation about classical diffusion, where the excitons would be anisotropic and they would be slow. This is what we see in most semiconductors. It seems that in this magnetic semiconductor, things can be a little bit different. Everything sort of that we see, every experimental signature that we found in this study seems to indicate that instead the excitons are dragged by the magnons because they move very fast, they move isotropically, they have this maximum at the Néel temperature. So that's all things that we wouldn't really expect from diffusion, but their coupling to magnons would sort of allow us to rationalize a lot of these things. So yeah, in principle, I think the direction of this work is, in this sense, interesting, that controlling the motion of excitons is not that easy. If you have electrons, you apply an electric field, you make them go left, you make them go right, whatever you want. Excitons are these charge-neutral optical excitations, so it's not very easy to control them. And people have tried in many different approaches, and a lot of them work too. So here we're thinking that maybe spin excitations, controlled excitation of spin waves, even using more traditional excitation schemes, might actually be a very nice way to sort of direct the motion of these excitons in a magnetic semiconductors. Okay, that's it. With that, thank you very much for not falling asleep, and yeah.